In terms of processes that we will look at processes that largely depend on pressure for densification. Okay, so you take a powder, you press it into a shape, and then you heat it to sinter it, and you get some finishing operations. Alternatively, you can make the powder and the shape separately without the pressure, and then you can just heat it to sinter densify. A hybrid process is when you apply both temperature and pressure simultaneously and create a end shape from the powder. So depending upon the process classification, the powders you can work with or the powders you need to work with can be very different. Okay. In this case, it is largely the powder by itself that needs to flow rapidly into a die cavity. Okay. If it does not flow fast, your throughput, the number of parts you can make per hour, is going to change. In this particular case, it is the mixture of the powder and the polymer that needs to flow as fast as possible in the mold cavity, and that is going to affect your throughput. Right? So how much powder can I pack into the polymer is more important than how much powder I can pack into the mold per se, and how quickly I can fill the mold. Right? Dry powder flow, powder polymer mixture flow, and then something in between over here. Okay? So what we have over here, different kinds of powder processes, different particle sizes. Right? And this says for any given, say for injection molding, typically you want to be in this size range to make it most useful. For die compaction, another process, you have to be at a higher particle size range. Right? So what does this plot tell you in terms of what is the best powder? If I asked you the question, what is the best powder you can work with? What is the answer? Answer is yes, it depends. It depends on what you're trying to do with it. Okay? You're not like smallest powder is not the best, largest powder is not the best. It just depends on what you're doing with it. Okay? And if you don't know what you're going to do with it, you don't know what is the best powder. What's the most suitable powder. Right? And so that is a starting point for us to understand. Why does it make it the best? We have not answered that question. And that's part of the logic that you build along, that this powder is most suitable for this process. How do they come up with the answer? In most cases by trial and error. And then after that figuring it out. Right? But now, this is for size. What about for shape? What about for packing? What about whether it's a tube or a sphere? Right? What if it is nano? Nobody knows. Right? This is stopping at 1 micron. What about all the stuff around below this? Right? How will we find out? Right? The thing is, most of manufacturing with powders has gone on without appreciating there's a dependency. From what is different from making pots and bricks from 5,000 years ago to making anything else like an electronic component today? One thing is you have better control over the chemistry and the particle attributes. Okay, so purity is a lot more. Second is there's an emerging logic structure that here is how what I make something out of and what I end up with are interrelated. And it's an ongoing process. Right? So part of your career and its success in working with powders depends upon understanding what's the sweet spot, right, with what I work with. Here's an example of how particle size affects sintering, right? So you sinter something, it becomes more dense, right? Density increases. You increase something, you increase the temperature, density goes up. Take a look at this graph. And now try to address the issue. If I change particle size, what is happening to the sintering behavior? Can you analyze the plot? Okay, so smaller the particle size, mo- density, or to get for a smaller the particle size, you can get the same density at a lower temperature, right? That's the other thing, right? So, in terms of now building off the theme, right? If you don't care about what powder you worked with, you have no idea what to set the temperature, what to set the furnace at to get a certain density or a porosity, right? You just have to keep. If you keep heating it at 1,000 degrees, you'll only get, and you don't care which powder you're starting with. You could get a density anywhere between zero point 0.5 through zero point 0.9, correct? And so, just if you keep blindly doing this without knowing what you started out with, you'll do a lot more trial and error than if you said, oh man, I have zero point 0.2 micron powder as opposed to zero point 0.8 micron powder, and so maybe I need to change the sintering conditions. And maybe that is the problem I'm facing in terms of porosity control. Correct? Another thing that happens with particle size is when you now begin to mix it with water or with a polymer, right? So either a solution or a melt. Here yield stress of the material is plotted as a function of particle size, and here viscosity is plotted as a function of particle size. Do you know what? So this is yield stress and this is viscosity. Without knowing what is viscosity of suspension and what is yield stress, can you see what changes if you change the particle size? What happens to viscosity? As you increase it, what is happening to viscosity? Right? Any idea why it might drop? Goes back to what you're trying to do. Smaller particles tend to agglomerate more, more agglomerates, more sponge-like effect, absorbing the polymer, higher viscosity. You know what is a yield strength? What does that mean? What's the physical property mean? Right? Share them.
When we stress, for example, we are having a material and we are stressing that material till certain limits, it has the ability to obey the law that we have, the
Elastic. Yeah. Yeah.
elasticity.
Which is what law? What's the name of that law?
And after that point, if you increase more stress, there is a yield point where you have the maximum stress. That point is
And
when
then you begin to deform, right? Where it begins to go from a solid like resistance to deformation to a more irreversible deformation, right? That is, you pour water out into the onto the floor. Now, if you straighten out the glass, it's not going to come back into the glass, correct? It's irreversible. So, at what point can you keep deforming the powder polymer or the powder water suspension such that it's no longer solid-like in behavior? It continues to flow, right? Main thing is these depend upon particle size. For instance, it also depends on dispersion, the chemistry of the dispersant, and things like that, right? Next thing is particle size, and so one of the main things is we saw that, for instance, the Stover process, right? You can get very uniform spheres, right? We saw that with silica, right? Lise, right? Stover process, you can get very uniform particle sizes. So that's going to have a certain packing behavior. Now you begin to put smaller particles in, into the space between that, right? You're going to increase the packing density, right? So in this case, if you have only two different particle sizes, it's a bimodal distribution as opposed to a monomodal distribution, right? And you can take it to the logical extreme where like you have a continuous wide enough continuous distribution till you have, right? Alternatively, you have perfect cubes, and like bricks you hold them and you can get like complete packing, one packing density of one, correct, if you can align them correctly. And the advantage of trying to work with nanoparticles, for instance, is maybe you can control those surface forces to the point where the system wants to automatically get into a particular state, right? So that's what we're trying to go after. So packing behavior and how that affects, not so there's not, it's not possible to have use just one single number to distribute to define how big is a particle size. You need to define distributions. That becomes the next type of approach. And here's a frequency distribution of the particle diameter. And in this case, it's like a wide distribution with coarser particles over here. And the red line, right, is a smaller median diameter and fewer large particles. And so just so where's titanium dioxide used? Where are some places that are used? Titanium dioxide is used for what kinds of applications? Catalysis is one, paints is another, rutile is a common, right? Biocompatibility is another place. But see, if in this case, in just terms of how it scatters light, right? If you have smaller particles, you can have greater opacity, and it blocks off light from affecting the coat, the part that is being protected from light, right? So that's one thing. So you need smaller particles, but gloss and durability and so on, and the brittleness of the film can be affected by the presence of coarser particles. So depending upon what final property you want to achieve, in this case for pigments, you had to adjust the particle size. So in the previous case for sintering and rheological behavior, we were talking about how particle size affects processing. In this case, we are talking about how particle size can affect the final properties of the application. So for instance, if you have to relate it to the clay nanoparticle and its dispersion, can you say some things about how that is important? The particle size of the clay platelet compared to the final application property. Yes, and then it can affect all the damping properties, the right, and the impact properties. Yes, right. So functionality of the end product as well as attributes while processing all affect by how your chemical parameters affect the particle size, right? So where you start out with and understanding that has impact through the whole downstream. So for instance, suppose Jupiter took the zirconium dioxide particles that you created and used it in his fuel cell. The energy output of that fuel cell is going to change depending upon the particle size you started out with and how Raphael is going to control the porosity. Okay, so size, right? Okay, we can say that for uniform monosize, if it's all a sphere, we can say this is diameter. But if it's irregular shape, what is it? Is this the size? Is this the size? Is this the size? What is the size? Right? What do we mean by that number? That becomes a challenge, right? So irregular shapes is not that easy, and so most of the particles that you're working with is irregular shape, and so then how do you define size for that, right? So there are many different ways in which you can look at volume per, you can look at the area, you can look at some dimension, you can express that dimension as a function of these possibilities, right? So not so straightforward, and so what techniques will allow you to do that, right, becomes important. You got to specify shape and certain lot of different features. So as the particle shape becomes more complex, defining particle size becomes more and more of a challenge. Right? The thing is, you need to all the way from 1 nanometer to about 1 millimeter, right? Over 6 orders of magnitude, they're all particles. So you need a whole lot of different characterization techniques. Right? Now, depending upon the particles you use, you might be using one or the other, or maybe something else. In this class, for the scope of the class, since we're talking about processing, we won't talk so much upon the methods per se, but we're just saying that there are different ways to be able to deal with different sizes. And so here are different kinds of optical, like through X-ray, so different wavelengths, right? And some physical methods as well that you can measure particle size. And different techniques are useful for measuring different size ranges, right? So if you use optical techniques, you can't get to very small particles. It makes sense, right? So then what do you use? Or if you use something like this, it's not very useful if your particles are too coarse, right? So knowing which technique works best for which size range is important. And sometimes, right, I mean, especially if you want to really understand the relationship between the synthesis procedure and the final particle size you get, or the particle size and the final properties, right? You might need to use multiple techniques because each technique is going to give you a slightly different result, right? So depending upon the measurement technique, what number you report can be quite different.